Physics is always part in our everyday lives. One good example is the motion of objects. The vehicle that we ride to arrive at work, people walking along the street, and more importantly, the Earth and the Moon are in motion resulting day and night. In this video, we will talk about object's position, distance, and speed with respect to a reference frame, and displacement of an object as it changes its position. It is very important to specify the reference frame when stating speed or distance of an object. For example, Mr. Bean is in the train. The train travels 85 km per hour. Mr. Bean walks at the speed of 5 km per hour towards the front of the train. Mr. Bean's speed is 5 km per hour with respect to the train as the frame of reference. But Mr. Bean is actually moving 90 km per hour with respect to the ground. That is 85 km per hour plus 5 km per hour equal to 90 km per hour. In physics, a coordinate axis is used to represent frame of reference and direction. To apply this concept, let's define what is displacement. Displacement is simply the change in position of the object, or how far does the object move from its starting point. Here's an example using the coordinate axis. Peter Pan is flying 20 meters to the east from Neverland. He heard Tinkerbell calling his name, so he turned around and fly back 10 meters to the west where he meet Tinkerbell. The total distance traveled is 30 meters. While the displacement is 10 meters since Peter Pan is now 10 meters away from Neverland. Displacement is just equal to 20 meters minus 10 meters, which is equal to 10 meters. Must take note. Displacement has both magnitude and direction, and is called a vector. Thank you for watching. I hope you learned something from this video. Basketball players move everywhere in the court during the game. The most aspect of their motion is how fast they are moving, which bring us the idea of speed and velocity. The terms speed and velocity are often used interchangeably in ordinary language. But in physics, they are different. Speed, or in general, the average speed, is the distance traveled along the path divided by the time it takes to travel this distance or elapsed time. On the other hand, velocity, or average velocity is defined in terms of displacement, divided by the elapsed time. Consider this example. Stephen Curry run to the center of the court for 15 meters and then, run back 10 meters. Suppose this took 10 seconds to complete. Now, let's calculate the average speed of Curry. While the average velocity is Now, it is apparent, average speed and average velocity has very different magnitude. Quantities that has magnitude, as well as direction are called vector quantities. Examples are velocity, displacement, force, and momentum. On the other hand, quantities that has no direction, but only magnitude are called scalar quantities. Some of these quantities are mass, time and temperature. Diagrams are graphical representation of a particular physical situation, is important and helpful when dealing with vector. Simple arithmetic can be used in adding vectors if they are the same direction. But when vectors are not along the same path, geometry is applied to solve such problems. For example, suppose Levi walks 10 kilometers east to reach Walsina, and then walks 5 kilometers north for the Trost. The displacements can be represented by this graph. The arrow labeled D1 is the displacement to the east, while D2 represents displacement to the north. Pythagorean theorem can be applied in this situation. Using the given, the resultant displacement is equal to 11.2 kilometers. It is common in physics problems to ask the components of a given displacement vector. For example, vector v is a displacement vector points at 30 degrees north of east. The positive x-axis is the east, denoted as Vx, while the positive y-axis is the north, denoted as Vy. Now, the vector components are Vx and Vy. This actually forms a right triangle. The longest side is called the hypotenuse labeled as h, the side opposite to the angle is labeled as o, while the side adjacent is labeled as a. From trigonometric concept, for a right triangle, the term sine and cosine is now equal to these equations, which are used to calculate the vector components, Vx and Vy. If the displacement vector is 500 meters, then the components are calculated by manipulating the equation. Vx is equal to 433 meters, while Vy is 250 meters. To check the computed components, we can use Pythagorean theorem, given by these equations. Magnitude of relative velocities may differ in different reference frames. Meaning, it depends on how you look a moving object. Example, a boat speed in still water is 1.85 meter per second. The boat travels directly across a river whose current has speed of 1.20 meter per second. When dealing with relative velocity, each must be labeled with two subscript. The first refers to the object, the second refers to the reference frame. From the given problem, 1.85 meter per second is the speed of the boat in still water, so it is labeled as V, subscripts are VW. While 1.20 meter per second is the speed of the water with respect to the shore, that is the river current, denoted as V subscripts WS. Additionally, the velocity of the boat with respect to the shore is denoted as V, subscript VS. And so, this is actually equal to the velocity of the boat with respect to water plus velocity of water with respect to the shore. This convention is very useful and applicable in solving relative velocity. I hope you learned something. A car, as it changes its velocity, is said to be accelerating. Acceleration is defined as how rapidly the velocity of an object is changing. In physics terms, converting this simple definition into mathematical equation, average acceleration is just equal to the change in velocity divided by time elapsed to complete the said change in velocity. To apply this formula, here's an example. A car accelerates along a straight road, from rest to 75 km per hour in 5 seconds. What is the magnitude of its average acceleration? The initial velocity is 0 km per hour, since the car is from rest before acceleration. Using the formula, the average acceleration is equal to 15 km per hour per second. This only means that the car's velocity changes 15 km per hour in each second. In physics, it is preferred to express acceleration in meter per second squared. So by simple conversion of units, the acceleration is equal to 4.2 meter per second squared. Thank you for watching. Problem solving in physics is all about basic technique and application of your knowledge in algebra and manipulation of fundamental equations. Uniform acceleration in one dimension or motion in constant acceleration practically occurs in real life. We now examine how can we manipulate this simple formula of acceleration to solve other variables such as velocity, time, and distance. You want to design an airport for small planes. One airplane that might use this airfield must reach a velocity before takeoff at least 27.8 meter per second, and can accelerate at 2 meter per second square. If the runway is 150 meters long, can this airplane reach the required velocity for takeoff? Starting from the fundamental equation or formula for acceleration and velocity, we are able to manipulate the equation to come up with something that can be used from the given. By simply substituting the given, the airplane actually run 24.5 meter per second. This means that 150 meters as a runway is not sufficient, because it must reach a velocity of 27.8 meter per second. It was widely believed that heavier object fall faster than lighter object. Until Galileo Galilei originated our modern ideas concerning falling objects, postulated his own hypothesis, claims and analysis, experiments, and contributed to our understanding about falling objects. His hypothesis states that, at a given location on Earth and in the absence of air resistance, all objects fall with the same constant acceleration. The speed of a falling object is not proportional to its mass or weight. To understand, you can perform this simple experiment. If you hold a piece of paper horizontally in one hand, and a rock in the other hand, and release them at the same time, the rock which is heavier, will reach the ground first. But if you will repeat the experiment, this time crumpling the paper, you will notice that the two objects reach the ground nearly the same time. This is because air acts as a resistance to very light objects with large surface area, just like the paper. Galileo was sure about this. But in Galileo's time, experiments in a vacuum, where air is removed, was not possible. A thrown or batted baseball is moving through the air in 2 dimensions, is an example of projectile motion. When dealing with this concept, some factors such as air resistance is ignored. Also, we will not be concerned of how the object was thrown or projected, but only after the object has projected, and before it lands. Meaning, when dealing with problems in this topic, analyzing the object is done when it is moving freely through the air under the action of gravity. Hence, the acceleration of the object is due to gravity, acting downward, and has a magnitude of 9.8 meter per second squared. The projectile motion actually consists of velocity vectors pointing in the direction of the object's motion, with its components in dashed lines. But we will deal with that in our next video. If you want to learn more in physics, click follow for more videos. Solving projectile motion problems require basic knowledge in kinematics and vector quantities. Consider this example. Shaw drives a motorcycle speeds horizontally off a 50 meters cliff. How fast must the motorcycle leave the cliff to land on ground level below, 90 meters from the base of the cliff? It is important to illustrate or draw diagrams when solving problems that involve vector quantities, hence projectile motion. In making a diagram, must relate it to the coordinate axis so that it will be easier to judge the sign of the magnitude. Next, analyze the problem and list the knowns and unknowns, in x and y axis, since this is an example of two-dimensional motion. Time is unknown, so it must be calculated using this equation, very basic in kinematics. Then, the initial velocity is calculated, also using basic kinematics equation, velocity is equal to distance over time. The result is equal to 28.2 meter per second. Problem solving needs a lot of patience and practice to develop such skill.